bigger models that include more information and innovate over time. It's a class of things called paired comparison models. So it's one team against another, and then these pair play and these pair play, and it's kind of all together. The same thing is used for chess systems. So the World Chess Federation uses his chess pair comparison ratings now. So it's same things that come out of one sport gets used in a lot of different ones. So, but in any case, so short week today. We're talking about odds and relative risk and sensitivity, specificity, RC, other things related to conditional probabilities and how they get used in actual practice. Right. So there's a homework due. Previous solutions for the other ones are posted. I think the homework 2 will be coming back from the grader by Wednesday, so we should get that back to you and be more on schedule for getting those back on a short time frame. Right. Conditional probability is where this story starts. So the probability of one event given another one. So this might be read as the probability of B if A is true. Is the probability of both of them. A intersection B or B intersection A is the same over there. And the thing in the denominator is its probability of B. And so often we're interested in conditional probabilities. Sometimes conditional probabilities get reported based on studies, but a couple other things are very common. Relative risk, odds ratio, sensitivity, specificity, and there are really just different ways of looking at these things. Right? So let's look at an example. So this one is involving dogs, golden retrievers, and border collies. Larger dogs are susceptible to joint problems, and one problem is called hip dysplasia, which in older dogs causes problems with walking behind. This is the one today, and that one's from Friday. That has to
Oh, wait, do you have one for Friday?
Yeah, this is one. Anybody else need one? That's for Friday. The handouts in general are online, so you could get it there as well, but I'll bring some excess copies. So the dogs either had it or did not, and in this study they collected data over a number of years making different research veterinary centers. And so out of 46,941 golden retrievers, 3,995 had hip dysplasia, 42,946 did not. Border collies weren't quite as numerous, 5,228. 221 had hip dysplasia, but 5,007 didn't. Right? So you could look at a number of different summaries of this table, right, for comparing these two species of dog, whether they have hip dysplasia or not. Right? The probability of having a hip dysplasia among the golden retrievers, right, that conditional probability, so if this is H and this is not H or normal hips for them, would be computed out from a table like this, or just based on the fraction. So among the golden retrievers, 46,941. 3,995 has the problem, which is 0.093, or about 9.3%. Right? Among border collies, though, you could look at that conditional probability. Chance of hip dysplasia among the border collies. Right, they had 221 out of their 5,228. That's a rate of 0.042. One summary that gets reported for conditional probabilities for comparing these two groups called relative risk. What's the probability for golden retrievers versus border collies? You could report it the other way, one versus the other. Right? That is one summary that could go out there. Right? So if it's greater than 1, the risk, if we put this one over that one, it's going to be greater than 1, and the golden retrievers are going to have a higher probability. Relative risk, in general, is the probability of B given A over the probability of B given not A. In our application here, it's the probability of hip dysplasia, that's B, hip dysplasia, among the golden retrievers relative to the other group, the border collies. In this case, we only have 2 groups that we're considering, so it's that ratio. So this was 0.093 and 0.042. So the relative risk is 2.2. So the probability among golden retrievers is 2.2 times that among border collies.
That's a 9 right there, right?
This one's 9, this one must be a 9, it's not quite close. You can't take just 1 over to get the relative risk the other way. Right? Relative risk of the hip dysplasia. The relative risk of normal hips, you could do that for these dogs. Would be the probability of having normal hips among the golden retrievers over the probability of normal hips given the border collies. And so if you did that, computed that one, well, you're going to do the separate calculations for the probability in both groups. Right? It's just 1 minus what we had before. 0.42, so there's a 0.907 and a 0.958, and that's about 0.95. It's not 1 over 2.2, that would be closer to 0.5 or 0.4. But it's another number. It's very close to the, kind of, because they're large. The difference here of having probability is not judged to be as big, like relative risk. Because they're both about 0.9, and there's a little difference up there, kind of a percent difference versus either one is not so big. Doing it this way, though, it's a 50%, double, right? So it looks much bigger in there. And that's relative risk. Now, relative risk is reported. There's nothing wrong with reporting it, but it does have its limits, right? These data that are in this table is a big population study, right? It's many different things, right? So what if instead of these data, so relative risk has limits, has its limits in use. Right? Nothing inherently wrong with it as long as you know where data are coming from. So let's say instead of taking the population, you pick 200 dogs that had hip dysplasia. And 400 that did not. It's easier to find dogs that don't have it, so maybe you take a twice number for convenience, right? So you're going to do a study with 600. Well, some of those dogs would be, I'm going to erase these middle lines because I want to emphasize that we've done the study picking those cases. Right? And some of those dogs, if we're focusing on the border collies and golden retrievers, some are going to be one and some of them be the other. If it's split according to the rates in the rest of the population, golden retrievers, border collies, you get 189 here and 11 here, 358 and 42. So there would be 53 cases here and 547 over here. If we sampled this way, trying to enforce, that we got 200 and 400. Now the proportion of hip dysplasia in the golden retrievers, is that representative of the golden retriever population? Is it representative of the border collie population? Not really, right? We've done something to try to get a richer mix of this in terms of more balance, right? The balance is initially 9%, 4%, there's a small percentage across in this row versus this row. It's more like 7% or something like that. So if you're just randomly picking dogs, you wouldn't get very many that had hip dysplasia, right? So if you wanted to study a medical treatment, pain relief or something for dogs with or without hip dysplasia, you took a random sample, you wouldn't get as many. This type of sampling is called case control sampling. It would be used for this and any number of other diseases, right? Where there's a condition that's somewhat rare, and you can find a number of individuals. You need somebody to compare them to. So there's a larger population where you can easily find some of these numbers. So you don't take a random sample and you get something that occurs only 1% of the population, very rare. You boost it, so it's more, you sample from that group more often. If you use this here, the probability of hip dysplasia of one of the golden retrievers is elevated. It's just not the same as it was in the population. So 189 over 547 is actually about 34%. So it's not representative of the population of golden retrievers because the sampling isn't a random sample. It's something that you would use if you wanted to study the benefits of treatment of hip dysplasia versus not, or performance or lifespan or something like that between these two groups. Getting a more balanced sample makes a lot of sense if you want to compare those groups to something. Relative risk, so the probability of age among border collies is also elevated because of the way we did the sampling. It's 20%, about 5 times as much. And the relative risk, if you take the ratio of those things, is 1.7. It's not a good estimate of the population one because of the sampling. But you might have this sampling because it's a good study design for other purposes, but you don't want to use relative risk to describe the population of golden retrievers and border collies. Right. So an alternative that gets used outside of population studies is called odds ratio. Now an odds of an event P is the probability that B happens divided by the probability it doesn't happen. And you can do that conditional on being in some group. This is says event B. So if the probability of event is 2/3, what's its odds? One minus that, yeah, the probability of 1/3 is the probability of not B. 1 minus the probability of B is 1 minus the 2/3 is 1/3. So 1/3 is part of the equation, right? But to do the odds, you got to take the ratio of that, right? So, right, 2/3 divided by the chance that it doesn't happen is 1/3. And so we get odds of 2. In bookies and gambling things, they might say the odds are 2 to 1. Right? It's twice as likely to happen as it is to not happen. 2/3 versus 1/3. Right? If you had instead, say the probability of B, well, let's just call it another letter, just whatever C is say 1/4. What's the odds for an event C? What ratio would you take? Yeah.
1/4 over 3/4.
Yeah, exactly. 1/4 over 3/4. And so now the odds is 1/3, right? Or if you 1 to 3. So 1/4 yes, 3 times as much no. So it's 1 to 3. And so we can look at the odds of having hip dysplasia among these two groups. So the odds of hip dysplasia among the golden retrievers, again, we can do this conditional, is the probability that we have hip dysplasia among the golden retrievers over 1 minus that. It's also the probability of hip dysplasia among the golden retrievers over the probability that they don't have the abnormal hips among the golden retrievers. And so there were 3,995 cases where it was yes divided by the total, and there were 4,2,946 where it was no divided by the total. Those two totals cancel, and so that's 0.093. Pretty close to the relative risk, but that's just kind of by chance. In any case, it's about that. The odds for the hip dysplasia among the border collies, right, the formula is probability of hip dysplasia among the border collies over the probability that we don't have that we have normal hips with those animals. Is that going to be higher or lower than for the golden retrievers? The probability here is about 0.042. You can do it either with the numbers or with percentages you got before. The opposite down there. So this is also 0.0. So it's really 92. 0.0. So I have there. 0.0. I have 0.093 here too. 0.907. I have 0.093 there. I'm just going to leave that there and see if it works. I didn't want to go back and check to see if my numbers are right, but it should be. I want to erase this because I'm not sure. I think maybe one of my numbers is off, but I'm not sure which one. So anyway, we'll leave it like this. So this would be 1 minus that, 958. When I calculated that, I got 0.044. A little bit elevated, right, versus just the probability. We're dividing by something that's almost 1. Right? The odds are really low, right, away from 1, away from even odds, because it's a small probability. Now the odds ratio is taking the odds for one group versus the odds in the other group. So the odds ratio for H, comparing the GR versus border collies. Now, I've not ever seen any conclusive notation about how people write that. It's usually in words and sentences. So, and I usually find it confusing because there's the odds are the chance that it happens versus the chance that it doesn't happen for one group. And this is the chance that it happens versus doesn't happen for this group versus that group. So it's the odds of hip dysplasia among the golden retrievers over the odds of the hip replacement under the border collie for the border collies. So 0.093 or 0.044, and it's 2.11. Right? So the odds of hip dysplasia are about twice as high among the border collies. Among the golden retrievers. One thing that's nice about this is that you get the same odds ratio even if you use that other table. Right? Now that other table, by taking a ratio to a ratio, ends up eliminating the fact that there's a disproportionate sampling. Right? And so it's still, so in the small table, had hip versus no hip, golden retrievers, border collies. That small table had 189, 42, 358, and 11. the odds ratio here, the odds would be 189 over 358 for the golden retrievers. For the border collies, it's 11 over 42, and that ends up being 2.11. It's the same. So even though this was designed as a case control, study, you can still estimate the odds ratio. Right? And it still is representative of the population. Things are the same, right? So that's one reason that this would be used in certain studies, right? As a different way of looking at things. Why did I compute the odds this ratio this way? Well, this was taking it a little more elaborate. This was what? So out of 600, this was 547. The odds for hip dysplasia among the golden retrievers from a table like this, 189 over 547 is the probability for 189, 547. And the odds, you divide the probability that it doesn't happen. So you divide by 358 over 547. And the count, the denominators counts in both cases. You get 189 over 358 as the odds in this table. That's not the odds in the general population, because again, it's not random sampling of the golden retrievers. It's sampling too much of that. But once you adjust by dividing by that other one, that disproportionate sampling kind of cancels, and the odds ratio is okay. So it is used. One place I use this is I was involved in one study of individual patient data, meta-analysis of a condition called bacterial vaginosis, and so some women were diagnosed with BV. Well, all the women were diagnosed with this condition, and some received antibiotics, and some did receive a placebo or no treatment in different studies. And the critical question was, did antibiotics reduce the risk of preterm birth? The outcome of interest here was preterm birth. And so our an odds ratio of 1 meant no difference. Equal odds, which means equal probability. Well, that's our null hypothesis, right, that we have, that we started with. That's how we set up the problem, assuming that there's no impact of the antibiotic in treatment. Well, there is an impact of antibiotics in treating infection, but did it translate into something in terms of preterm birth? So the odds ratio of 1 was a null hypothesis that says no effect, no reason to do it. Though as it was set up, the odds ratio less than 1 meant that antibiotics are associated with less preterm birth. They reduce the risk. Now it turned out that for one drug, metronidazole, that was used, the odds ratios were very close to 1. It didn't make much difference. But this other one, clindamycin, this other drug, on women who were at risk because they'd had preterm before or had elevated levels of some diagnostic criteria, it seemed to make some difference. But again, it was a little bit inconclusive whether it was significantly different, but the odds ratio was less than 1, which suggested there's a possibility that it did. But anyway, so odds ratios gets used in substantial things to answer these questions, right? But any questions about that example? So these are just numbers, right? There's odds ratios that are used there. We're going to define 2 other things that get used, right, in studies. that deal with conditional probabilities. Two other things that get reported with medical studies in particular. So two other probabilities. So in this case, we have the scenario is that we have a status of disease. So sometimes this is called a true, or it's true positive, or true negative. Somebody has a disease or not. And then there's a test, a diagnostic test that's done. The diagnostic test might come out to be positive, or might come out to be negative. And you could imagine having the counts of the number of people that are in each of these cells here. And one thing that gets reported, to summarize how well the test does, right, is among the people who are really have the disease, right, that are in that row, what's the chance that they actually test positive? Because you had a bunch of people that were clinically diagnosed, right, and you want to test them. You want the test to be almost certain that it's going to say yes, they have that disease. Right? If it doesn't say yes most of the time, or a lot of the time, it's not going to be that useful. Right? That is called something called sensitivity. There's a probability that somebody tests positive, given that they're true positive. That conditional probability, if these were counts of people, there's A plus B in this sample that are true, and A out of those tests, so A over A plus B, should be sensitivity. On the other hand, you want most people who really are negative. Clinically, they're negative, they don't have the disease. What do you want the test to show for them?
Negative.
Yeah, you want negative tests, right? That's called, the chance that happens is called specificity. Right, so the probability test negative, given that you're truly negative, is this other one. Right? So if these were counts of people, there's C plus D in this row, so the chance of being negative would be D over C plus B. So when is what would be characteristics of good tests? Yeah.
If both the sensitivity and specificity of that is high.
Yep. So we good tests have large values. But for many quantitative tests, right, there is a cutoff. Testing for prostate cancer, there's a PSA test, and then there's a cutoff level, 0 to 4 to 10, or there's some cutoff number. In the bacterial vaginosis example, there could be a bacterial cure, and there's a score that's associated with that. Is it above 7? Is it above 8? And depending on which cutoff you choose, it changes this table, right? Depending on whether they test positive or negative. Right? So each cutoff value for a test gives you a sensitivity and specificity. Gives you different conditional probabilities. That's why this is included with this. This is all conditional probabilities, looking at things different ways. And so one way that gets summarized is something called an ROC curve. Right? So ROC, the curve is on this. It plots two things, right? We have two things here. We have sensitivity on this axis. You go between 0 and 1. And on this one, it puts 1 minus the specificity. And 2 points that are possible are 0 here, 0, 0, and 1, 1. And the place that's good to be is back up here. Good tests have high sensitivity, and they have low specificity, which puts them back, 1 minus, that puts them in small values. This is a good place to go. But you could declare everybody to be positive, no matter what. That would get 100% of the people that truly have the disease right, but it would make all complete 100% errors for the other group. The other extreme is to say that nobody has the disease, which in practical cases won't make any sense, but it makes no errors for the group that doesn't have it, but it makes 100% errors for the one that does. So depending on the cutoff, it's possible to get a little frontier here, a little boundary that describes the performance of tests, right? And so each point on here can correspond to a different cutoff for a test that defines positive or negative. So ROC comes from a communication information theory field. This is called a receiver operator characteristics. And so it has really nothing directly coming from the medical field, but it was about communicating information. Right? That when you would send out information over a noisy channel, trying to communicate via radio or something across the ocean with a lot of static and things like that, right? If you could boost the signal or do something to it, you could do things to influence how clear it was. Right? And there's a chance that you would get a positive message and get it right, or a negative message and get it wrong. Remember, like Morse code would be like a series of short sounds and longer sounds, da 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 da. And so actually picking that up in a noisy environment is hard. And so that also has this: do you get the correct signal correct, right, or do you get the error signal in error, right? So it has that type of thing, and that's where it comes from. But what people look is kind of the area under this curve, and the higher this curve goes, higher curve. The curve, it means higher sensitivity. And it also means higher specificity. Right? It does that because it means lower 1 minus the specificity. Right? This 1 minus means that being up here is good. So you would probably choose one of these things, one of these cutoffs here, to achieve a certain sensitivity and a certain specificity. The book gives an example, and the handout gives another example. So let's look at that a little bit. And I'll pull up my copy, previous course. So, in this one. So now you can all just kind of like stand on the side, or no, I think I can turn it. So this was one example in Rosner's book, and I think it's worth explaining a little bit of detail that's in there. Right? So these were individuals that had normal or abnormal tissue. Right? And 58 had normal tissue, and 51 had abnormal tissue. There were 109 patients overall. And they had a CT scan, and they were given evaluations based on that. Anyway, based on that picture. Oh well. And 36 of them had tissues that looked definitely normal. Right? 8 had probably normal, 8 had questionable, 2 had probably abnormal, 35 had definitely abnormal. So that's judgment based on evaluations. They might be looking at something quantitative. They might be looking at something kind of more interpretive based on their experience. And depending on, you make a cut point here somewhere. Say probably normal. Say normal and probably normal is called normal. Your test would predict normal. Is that a good place to cut it? Call these people probably normal and call these people probably abnormal, and they need more investigation. Right? If it's strong enough, most of the people that are classified normal because they're far enough on this test will be normal. And most of the people that are defined as abnormal will be abnormal and be a good thing we ask them to get more tests, right? So depending on the test positive criteria, 1, 2, 3, and so on, we get different sensitivities and specificities. So if everything is called possibly abnormal and, based on 1, we don't miss any of the 30, we don't miss anybody, right? Everybody's called abnormal. So all 58 that are, well, all 51 that are abnormal are captured, and they're all sent for more testing. No error there. However, the ones that are normal, we also send them. So we get a sensitivity of 0. So that's not a specificity of 0. That would be an extreme. At the other point, the other extreme, we call nobody abnormal and say everybody's fine. That's perfect for the people who are normal, because they are normal. We got that right. For the other ones, we got totally wrong. You probably want to do something in between. Right? So you choose something like 2, right? That corresponds to a sensitivity of 94.94. Because of the 58, or 51, sorry, that are abnormal, right? 2 or, well, so 2, oh, I'm going the wrong direction. So something like, let's say 4 or more. 4, 5, 6, 4 or 5, probably abnormal or abnormal. We call those abnormal. We get 44 out of the 51. 44 out of 51 is our 0.86, 86%. On the other hand, there were 13 people who are normal. So 13, and then there's only this number over here, 12. So 45 out of 58 are correctly diagnosed. So that one would correspond to a 78. So each of those cut points, drawing a boundary in there, gives you both a conditional probability for one group and a conditional probability for the other group. And what gets done is you can make that graph for each of those cut points. So here's this ROC curve in this case, right, with the different points, right, on there. Or 1 minus, so 0.97 here, so 1 minus that is 0.03. 0.78, 1 minus that is 0.2. It would be helpful if there was one more column here, 1 minus specificity. And then you would see each of these points. So you want to choose something up here that is pretty high. If you wanted to get more than 70% for each test, more than 70% specificity and more than 70% specificity, what should your cutoff be? What should be the rule for classifying people? We did it with this in here, right? 4 plus, 4, 5, or 6. And so 86 up here. Where is that? 86 going up here. So about this, we choose that test there. Right? And that would define our criteria if that's what we thought. And one way this gets summarized is to calculate the area under that curve. One thing the book shows you is that, this is actually a trapezoid. These little things are little trapezoids here. So it has one little example in the book where it says we use this trapezoid rule to calculate that. And what it's doing is calculating the area in that section, and in that next section, and so on, and in this section, and adding them up. And so it adds up the area, we get 0.89. And says there's an 89% chance that this type of test is going to make a correct diagnosis. I'm less swayed by this ROC area under the curve business. I think it's more important to have an actual specificity and actual sensitivity, because that's going to be your rule. Not an average rule, but your actual rule. Right? So anyway, but things are compared. So if you had to change the way, if you've gone from a CT reading to an MRI, right, you might get different numbers up here. And you'd have one curve for MRIs, one curve for CTs. And if the MRI was higher, that's going to be better diagnosis. So, but primarily, we will do a single cut point and say what's the sensitivity, specificity, or the odds ratio for good versus bad. Any questions about? So beyond that, this is another page from a book called Applied Logistic Regression. It would be, of course, a topic we'd probably talk about in Statistics 451, which is advanced methods, or would be possibly covered in a first course in graduate school. If you're trying to do medical statistics, they would talk about logistic regression. And this is classified, oops, right. They're doing something called logistic regression. It's predicting a probability. And so in this prediction of probability, we get if the probability is high enough, we're going to say this person probably is reusing drugs in this particular case. And this particular probabilities account for age, health status at the initial time period, male, female, and a number of other dimensions. Right? So all this goes into estimating this probability, and that's called logistic regression. But at the end of the day, they make a cut point. And some people are classified as probably using drugs, and some are classified as probably not. Right? But there's a truth, right? And so in these studies, they had the true drug-free return to drug use. So this is truth. And then they have this classification. And the classification might use a cut point of 0.55, 0.6, and so on. Whatever the cut point is, you get a different sensitivity and specificity, or 1 minus that. And so at each cut point of that probability, you get these two conditional probabilities. You can make that curve, that ROC curve. See, they're both changing as the cutoff changes. Sensitivity goes up, and sensitivity goes down. They're switching. It's kind of a trade-off. Do you predict well for one group that's truly positive, or one group that's truly negative? And depending on how you move it, you change that probability. So anyway, this is the ROC curve that's implied by that in this example. It's using a more elaborate statistical model to estimate it, but the goal is still the same as these other problems. Right. Not that you have to know anything particular about logistic regression or anything like that, but given a table like this, we might calculate predictive sensitivity or specificity based on one set of numbers. But it fits into that bigger picture. But any questions about that? We will look at one more numerical example to illustrate some of these things, but that's what's going on with that. So what type of topic do you want to do for another example? Smoking and lung cancer, something related to depression and suicide, immunology. A lot of these get used in different. Maybe let's do the mononucleosis. Do that as a medical. So let's say that so one treatment for mononucleosis infection is tonsillectomy, or at least it was used at one time, tonsillectomy. So if tonsils become affected and the virus is in there, it can recur. This is from a book called Biostatistics Casebook from 1980 by somebody named Rupert Miller, who was one of the founders of the statistics department and biostatistics department at Stanford. And so in this, they give this example where some people have infectious mononucleosis, so that's IM, or their control, they don't have that infection based on assay and things. So there were 185 individuals that had it, 655 that didn't, for a total of 840. Some of these individuals had tonsillectomy, and some did not. 275, 565, 40, 145, 235, 420. So we could ask a question, is there an association between tonsillectomies and infection, or infection and tonsillectomies? And that's what we're really doing, is with all these different things, relative risk, odds ratios, comparing proportions. Are these two things associated with it? So what's the probability that we have infectious mononucleosis among those that have tonsillectomies? So a little bit much for me to write all that out, right? But I'm asking, what's the chance those with tonsillectomies have infectious mononucleosis? Right? So it will be written as a sentence on some type of exam or something. Yeah, 40. So there's 40 individuals, right, that have both. So that will be the numerator. But what's the denominator?
275.
275. Right? The group I'm considering, or the one I'm conditioning on, they have a tonsillectomy, right, is that fraction. 0.22. What's the probability of, what else do I do? Tonsillectomy. No, that's not the right. My numbers, that's not right. I calculated something else. But that's what you would calculate. It's about 1 in 7. Or 275. What's the chance of this among that they did not have a tonsillectomy? So in the column, they have no tonsillectomy. 145 over 565. So what's the relative risk of mononucleosis among these two groups? So the relative risk of immunomononucleosis among the T versus that would be going to be the probability of one of these over the probability of that given they're not having that. So it would be the 40 over 275, which you could calculate on your calculator as one number, and then 145 out of 565 as the other number. And so this number is what, about 1 out of 4? Because 4 times 14, 145 is about 560 or so. So this is approximately, I'm sorry I don't have these numbers exactly. It would be about 470. So that would seem like it's less likely among those that do not have a tonsillectomy. So if the story behind this is that the people that have had the infection, get the tonsillectomy, this makes sense, right? That there's some association. If you've had the disease, then you're more likely to get it. Or if you're looking at it, you have a sample of people with tonsillectomy versus no tonsillectomy, right? Then what's the chance that they had the immunomononucleosis in the past? And it's less likely if you've actually had the tonsillectomy. Maybe it's protective for it. That's one thing that you can compute. How about the odds for tonsillectomy among those that have IM? Does the probability of tonsillectomy among those with mononucleosis over the chance that you don't have that with mononucleosis? A little bit different from the other one. Different denominator. There's 40 individuals who had both, but now the denominator would be 185 because it's asking among those. That's about 0.22.
What about the bottom?
Bottom, there's 145 here, was out of the 185, right? It's 145 out of the 85 that did not have it. So looking at the table, out of this 145, you have some yes and some no. So we get an odds of about 0.22. how about the odds for tonsillectomy among the do not have? If they do not have this, they're called the control group. So it's a probability of tonsillectomy among those that do not have the infection, the history of the infection over 1 minus that. So in this group, there were 655 that did not have the infection. 235 of those had tonsillectomies, whereas the 420 didn't. And so that ratio ends up being about 0.56. Quite a bit different than the other ones. The odds are much higher for tonsillectomy among the group that did not have the disease. So there's one measure of association, right, would suggest that people that don't have the disease are less likely to have tonsillectomy. Well, they actually are more likely to have tonsillectomy. So maybe the tonsillectomies prevent the disease or something. So the odds ratio for T, now this is versus not among the IM versus IM, the ones that don't have the infection. Right. I don't, it's not, sometimes in the medical field things are written and it's just like the odds of this versus that. It's like, okay, there's two things in the numerator and and then two things in the denominator. And so I always like to specify that it's this versus this in this group versus this group. Because then I kind of write everything. It's hard for me to keep track in my mind quite as well without actually writing it up. Maybe that's the difference between going to statistics or biostatistics program. Biostatistics, you actually learn to think in this a little bit better, right? So it would be the odds for this group, right, versus the odds of this group. So if it is 0.22 or 0.56, so the odds would be less than 1 because the odds are higher in this group that we're putting in the denominator. So the odds ratio, whatever that, 2m, 1.5. This is I didn't finish this one. This is 0.22 over 0.78. So this is 0.28. So this one, sorry, this should be 0.28. I didn't quite get it all the way. But that's the final answer on that one. So this is about 1/2. So the odds are about half in comparing these two groups. So that would suggest that these things are associated in reality, not random. Right? So we could do sensitivity, specificity, if we could think about how we wanted to do that in this case. The other type of thing that all of these things, these tables can always do, so you can always come up with one of our 2x2 tables, we turn them into trees. So we could split this into the mononucleosis group and the control group, and we could do the chance of T versus not T here, tonsillectomy versus not. There were 22%, or 185 out of the 840 that were that group. That left 78% over here, so 655 over 840 there. And then some of these probabilities that we computed before would come in. And we may not run through it all, but we have kind of a setup for doing the 2x2, the table, the probability of one of these endpoints, IM and T, or maybe Bayes' theorem. Right? So there's all these different ways of looking at conditional probability and different interpretations, different ways of presenting it get used. But if you understand the general concept, that there's some denominator and then something that you're putting in the numerator, then you can read a lot of literature. And a lot of reporting that's out there on disease and rates of things. Any questions? Good. It'll take a little bit to work through carefully, which is the denominator and so on. The differences are a little bit subtle. Keep track of it. Let me save this. Let's have homework for a few people. So John Curtis, John, Gabby.
I
think
just
I
gonna
went
run around
homework.
the package real quick, but
That's
what I did.
Yeah, that works.
It was like,
Yeah,
it was like that weird time when our passwords didn't work. So, none of us.
Oh, really? Yeah, if you want to jump in.
And,
When do you have practice? 3 o'clock.
yeah, because my email wasn't working very well, so it wasn't really sent.
Okay.
So I thought I sent it, but it probably didn't go through, so.
Well, I might have it. It might
Yeah, and also, I was like, my handwriting is kind of small, so that's the scan probably didn't get well.
Okay.
If it did.
You guys need to wait.
Sorry.
Well, no, thanks. I just want to make sure you get credit for the work you've done and. No, thank you. Yes.
I was just gonna listen to what you said
Yep.
about the homework, because I was a little stuck too.
Okay, so this one is about, sure, it's like the Alzheimer's,
Uh-huh.
and I remember on the handout you said like how they're like 3 independent things,
Yeah,
and I wasn't really sure, like, because we didn't really go over that in class.
so much. So yes, there's 3 people,
Uh-huh.
77-year-old man, 36-year-old, and 88-year-old woman.
Yeah, so they're like, 2 of them are like in the same age group, but they're also in like 2 different genders, so I
Mhm.
wasn't really sure like how exactly.
So if, say if you had 3 people, right, the chance that, so you had one person here, one person here, one person here,
Mhm.
these are the chance that they individually have it. So the chance that all 3 have it, or you can multiply the probabilities of those together.
Okay.
That's the independence.
Oh, so like I would
Or-
find like the chance of him having Alzheimer, like, okay, like for that one person, and then the chance for that one person, then that third person, and
Yep,
then you multiply
yep.
all of them together.
Mhm.
How would you do for the individual person? Do you just divide it by their?
So if an individual person, it's just the probability that.
Oh, so it's
given
just that
there.
number?
Yeah, that probability.
Okay. So when you're looking for
per-
all 3, you just multiply
100,
like
yep.
all 3 of them.
So that you
together?
don't, yeah, so you don't have to do any more math besides that.
No, if they don't have it, it's gonna be 1 minus that probability,
Oh, okay.
right? So if 4.9%, 0.049
Mm-hmm.
have it, then 95.1 don't.
So you just take like whatever like age they're in and that, like say if it's like that 2.2 and like 4.9 and multiply those all together.
Yeah, so if they all have it, now if it says a question like one of them has it, right? The man could have it, or the one woman could have it, or the other one,
Okay.
but the other 2 don't.
Then you just add the 2 or multiply.
You're gonna
the
have
two
kind of
together.
3 scenarios.
Okay.
Where you're gonna, each one of those, you're gonna multiply 3 numbers together.
So like, for like you would do 3 different like math, like multiplications out, okay.
Yeah.
So you would do like if one didn't have it, but the other, or the one did have it, the other 2 didn't.
Yeah.
But like 3 different times?
Mhm.
Okay, that makes sense.
And you just
Okay.
multiply it all together.
You multiply those 3.
Yep.
Right, and then you multiply the next 3, the
Alright.
next 3, you
Mhm.
add those 3 things together.
You add them all
Yeah.
together?
Okay.
Okay.
So the, giving one person could either, there's 3 different ways it could happen, right? So you get the probability of this one, and this one, add
Okay.
them.
Okay. Okay, that makes sense. Thank you.
Good. I think I'll probably get some more questions.
Yeah.
Thank you.
Yeah. Bye, have a nice day.
You too.